All right, on to chapter 18 of the Fourier transform. We're just going to move through a number of topics here to kind of illustrate or maybe show more of what the Fourier transform, where its strengths lie, and where you can use it best. So let's look at the definition of the Fourier transform. Now the first thing here is the series is becoming a transform, right? Remember in Laplace we started with just a math description, but then we developed the transform. And we really want to do this in a lot of things, right? Just find the transforms so we can deal with networks and circuits as arbitrary boxes. All right, let's consider this signal, a periodic signal. So this, we'll start with just graphically trying to describe important things that are going on. So the transform, or the Fourier series, is really about periodic functions, right? That's what we're talking about, periodic functions. And yet there are a lot of functions, a lot of interesting functions, forcing functions, that are either not periodic or have periods that are so long that kind of makes them difficult to analyze in traditional ways. So the first step is we could say, what is this? Well, this is a periodic signal, right? With period, what have we got? Period, here's 0 to tau and 0 to t with period t. Okay, it repeats back here in the negative direction, also in the positive direction. Okay, what if we spread that out to where we've really just got one piece of size tau, right? This has a duty cycle up here of tau over t. Here we're just looking at, so we pushed these two, we pushed this way out that way, and we pushed this way out that way. So all we see is this apparently non-periodic signal. Well, the first thing you get from this is the idea that, oh, maybe I can represent non-periodic signals as periodic signals with a really long period and short duty cycle, small duty cycle, all right? So let's take a look at what happens to this, the Fourier transform of this. If I have, so here's a 20% duty cycle with a t of 1, a period of 1. And on the right, we have the Fourier transform of this. So we saw in the last chapter, right, that the coefficients of this, the c sub n, were equal to what? Something 2 times, we got into this sinc function, right? The sine of n pi. We did this example over 5 over n pi over 5, where 5 was the relative number really based on the duty cycle, right? This duty cycle is 20%, right? In this case, it's 1/5, right? So that's where we're seeing the 5. So what's going to happen as we push out the other pulses? Now here we've just eliminated even pulses or odd pulses, depending upon how you want to reference them. And now we've got a duty cycle that's what we can say here. Where am I at? We've got a duty cycle in this one now that's what, 0.2 over 2. So that looks like 1/10, right? And if you look here, you'll see, oh, it looks like we're doubling, right? There's in this space here, right, we've added another frequency component. Okay, so we've filled in more frequency components, and in fact, as we really push them out, right, so this now has a duty cycle of what, 0.2 over 10. So the previous one was 1/10, and we multiplied that by 5. So this is about 1/50th, okay, related to the first one. So now we've really filled in a lot, right? Filled in a lot of frequencies here. All right, one thing you might observe, magnitudes, by the way, are down if you look. This is less than this, which is less than this, okay? So one thing you might observe here, we have to add a lot of frequency information. We're talking about the amount of information it would take to reconstruct, if I had to reconstruct this waveform versus this one or the original up here. And so what happens as the periodicity goes down, the period gets longer, so it looks more like a non-periodic waveform. You really have to add a lot of frequencies in order to essentially shape the waveform. Okay? And this is a very, I'm not going to go on about this, but this is a very important observation, moving from here to here to here. The addition of all these frequencies in order to create this waveform, if I had to recreate it, do an inverse transform, means I need there's information packed in all these frequencies. There's always the basic frequency, right, the fundamental. But I need all this additional information in order to shape the edge of it, the high frequencies. This is a commonly recurring idea in signal processing and information theory. All right, so let's start with the exponential version of this versus the sine cosine version. Okay, so here is, we developed this in the last chapter. The function is expressed as the summation, right, now over from minus infinity to plus infinity over the whole range of some c sub n. So we derived this out of sine and cosine, the a sub n, b sub n thing. We had square root of a sub n plus squared plus b sub n squared. And so we're back, really relying on Euler's identity. And here we are with that, calculating c sub n's over one period, right? And we split it between minus half a period and plus half a period, right? Minus half a period and plus half a period for any f of t, right? We found this was the way to obtain the coefficients. And in this exponential form, we have what's called the fundamental frequency, the fundamental harmonic. It's not really even a harmonic. It would be the n is 1. So that is just simply 2 pi over the period, which of course is the same as, what is this? This is actually 2 pi f in disguise, right? All right, so we have that. And the spacing between them, that's what I was just pointing out in the previous picture. The spacing is just this. It is simply, n plus 1 times omega 0 minus n. So what is that? That's n plus 1 minus n omega 0. So that just comes to omega 0. And we're right back to this. The harmonics are spaced at even multiples of integer multiples of the fundamental. Okay, nice stuff there. Now, if we take c sub n's and plug them into the f of t, we do all that, we get this. Right? F of t expanded then is the sum over the full range, plus and minus to plus infinity. And now pull out. So here's our 1 over t, right, that we had. That came from here. So we can safely pull that out. And it's now the sum of the integral over individual periods of the f of t. This is still part of this, right, times e to the, which is part of this, right? This is just a simple plug-in and make sure we collect all the terms in the right places kind of thing. And we'll do just a bit of massaging or rearranging here. So the first thing is we're bringing in a delta w, right? That recognizes the spacing. So this is bringing back, just our changing time for what the inverse of our fundamental frequency, all right? And pushing things around a little bit more, we pull out the 1 over 2 pi. Nicely put our delta w way over here, right, as we set up to change things in the next step. So next we're going to then replace we'll make these replacements here. We're going to replace the summation by the integral. As you might have anticipated, the delta w is going to become dw. And any n times the omega 0 is spacing, so that's going to be, I'm sorry, that's not spacing, that's the absolute frequency, so that becomes w. So this will take place for any of the given frequencies. And plugging that in to our original f of t, we're now working from the bottom here, right? We're coming off of this. And we have our 1 over 2 pi. Now our summation is replaced by the integral, an integral inside. So we've got an integral of dt, and now we've got an integral of dw. Okay, and on doing that, we end up with a Fourier in the frequency domain, Fourier of omega. F of the magnitude of f of t becomes just this, right? Which is an integral over t. Very nice. All right, so the inverse also exists. F of t will be the inverse of this side, right? The inverse of this. So that's going to be 1 over 2 pi. We're just going to take it in the other direction. And the integral now in the frequency domain, right? And here's our omega t. So now in this case, t is a constant, and omega is the variable. Up here, omega was the constant, and t was the variable. All right, so you kind of can see the back and forth then between, it looks very similar, between the frequency domain and the time domain. And so we can just say, there's a relationship. We have here both the transform and the frequency. So this is the series in t, and this will be what? A series in omega. Okay? Important thing, convergence happens only if this function converges in the time domain, right? If the function itself doesn't converge in the time domain, less than infinity, then we're not going to have a transform. We're not going to have a Fourier transform. All right. So now, just as with Laplace, there are properties of the Fourier that are valuable, good to know right up front, and then we can just rely on them, pull from them, help derive Fourier transforms, knowing certain properties exist. So here's the list. Linearity is the first. We're going to talk about each of these, move through each of these, and show the the key ingredients, so to speak. But linearity, you know, something something is linear if I multiply by a constant, and I add things. You know, the linear equation y equals mx plus b, linearity. Time scaling, right? We're going to want to be able to take a Fourier transform and recognize, ooh, that's the transform of something that I have. The only difference is my time frame is different than that time frame. I want to be able to scale. Same thing with shifting. If I need to shift it plus or minus in time, it's like well, a time shift is like a phase shift. But and some of these, by the way, time shifting is one that sets up. If I have two waveforms, but they're out of sync with each other, I could but they're basically the same shape. If I could time shift them, I might be able to just then apply linearity and add them. Frequency shifting, this is also amplitude modulation. And yes, that's just like AM radio. AM radio is about frequency shifting, interestingly. It's the amplitude. And yet it relates to, as a mathematical property, it relates to frequency. Time differentiation, it's the differential. We'll have more to say about that. Time integration, so differentiating and integrating in time. There are properties of that that are present in the Fourier transform and useful. Reversal, we'll see about this. It's fairly simple, but if you reverse the image of something, does that, you know, what does that transform look like? Duality, and we know the dual of functions. We're going to put some legs on that with regard to the Fourier transform. Oh, here's one that's, you know, valuable around all over the place, but also at times kind of confusing and mathematically frustrating, but very graphical and visual. Well, it occurs in the Fourier as well. Why not? It's just a mathematical property. So we'll be delving into all 9 of these. And let's begin the list with linearity. Here we are. We can multiply by constants and simply add 2 functions. Turns out we can do the same with the Fourier transform of those guys. Okay, so the transform here on the right, this looks, what I love about linearity, of course, it looks just like the time domain part, right? You just substituted this for this. All right, this happens. Why? If we take the Fourier transform in the time domain, it's the integral of that function, e to the minus j omega t in the time domain. And if we put that all together, what happens? Well, it's just the separate. This, because of linear, allows us to separate into 2 parts. And so now we're really right back where we were with individual, right? If we pull this out front, this is a constant. The rest of this is just the definition of the transform, and same with F1. Okay? We would expect that. So we can quickly write it as it was described in black at the top of this, and off we go. All right, here's an example. Sine omega t. Omega 0 t is what? We already know. We did this from Euler's identity. We did something like this already. And we know that the transform of the sine then is 1 over 2j times the transform of the individual functions summed, well, subtracted. Okay, and the coefficients, a1 and a2, are just 1 in this case. And so we go for, if we have the Fourier transform of e to the j omega 0 t, then we've basically created the Fourier transform for the sine. See, now one would think, well, linearity, that's obvious. You know, we would just do that. But here's an example that shows you how you take linearity, here and apply it to something that was only a single function to begin with. So this is almost like a decomposition. If I find some combination of simple functions or functions I know that when put together with the proper coefficient or whatever was necessary, I get back to something I want to know here, namely a trig function. Okay? And so if we run all that out, right, the individual Fourier functions, we get this, and we're back to what? Those are delta functions, right? Two delta functions. And when we finish all that out, bring the j up to the numerator so it becomes minus j, right? What have we done? We just simply reverse the signs here, reverse the signs inside, and we get this, okay? We know that. Next one is time scaling. In time scaling, I mean, this is the end result here. So what we're really talking about is f of omega, right, corresponds to, whoops, not that way, corresponds to the transfer, or the, I guess I could say it's the equality, but it's the Fourier, how do I make some fancy f here, of the function f of t, right, f of t. Right, so that actually is equal. It's not like goes sort of like that. All right, so why is this? What are we doing here? We're just substituting for t, we're substituting at, right? We're coming in here and saying our f of t, I guess I could be saying something like f of x, where x equals at, right? Something like that. All right, so here we are with this, and we're just describing as though I didn't have this first line, because I don't. I'm saying the Fourier transform of f of at, and I'm just spelling it out explicitly here. This is the starting point, f of at times e to the minus j omega t dt, the integral of that over all time. And so that transform equals what? See, here's the substitution I just made. X, where x is at, fixing everything up according to that. Dx then is what? T 1 over a times dt. If we want to work it backwards, we just have to try to, do all our accommodating of constants and coefficients here. But look, that ends up pulling out the constant 1 over a, and now we're dealing with, whoops, here it is here, our omega over a, which is what goes in here. All right? And we know from then, if we have an f of if we have a rectangular pulse here, right, that's what we've got. So this is the rectangular pulse. And here we are looking at our sinc function, okay, of a certain period. And what are we talking about with time scaling? We want to change the period, all right? So if we want to change the period to 2t, what does our relationship tell us to do? Take 1 over a. Well, this was the original thing, so now we take it by a, so that's dividing by 2, but then we have to modify the frequency also to be dividing by 4. All right? Now, let's take the first case where p of t looks like this. So t is a between minus tau over 2 and 2. All right, so this is, remember, this is the pulse, right? That's what I'm looking at here. I'm looking at a pulse. This is the description of the pulse, right? And this is the Fourier transform of it. All right, so we have that. We've actually seen this before. Now what we're doing is doubling the doubling the time, the period. All right, so we're saying that 2t falls between, notice this, 2t falls between the original period window here and here. So that means the integral doesn't change. So time is between tau over 4 and 0 otherwise, right, for the magnitude. So here is that. Now let's look. Let's compare the two. What has happened? This has fallen, right? This is lower. A tau over 2 is less than what was back here, right? This is less than a tau, right, by the factor of a. So that's smaller. But this has now, I don't need that. This has now moved out to what? Where we've got minus 2 over tau. So we've spread this spectrum, even though what have we done here? We've narrowed it, right? In this is narrower. Okay, we're going to be talking more about this especially when we get to some of the other properties. Okay, so we need to do another one, time shifting. Looks like I wrote over a little too much. So time shifting is just what we've always known it to be, the Fourier transform. Here we are time shifting, right? So what is this doing? This is actually pushing the time to the right. Correct? If I need a larger t in order to get f of 0. That's how I think of it anyway. So the end result is that time shifting is this, when it's in black like this. So here's the time shift. And here's the original. Here's the original, the unshifted transform. All right. So how does this come about? If I try to develop that transform, the Fourier transform of that is what? Let's go back to first principles. The integral between minus infinity and infinity of now, here's just the new function substituted in. All right, and we're going through the transform process, developing the transform. So what do we do with that? Same deal again, substituting x equals t minus, this is just a routine mathematical, I was going to say trick, but it's really a tool. When you have something more complicated like this, just make a substitution, and as long as the substitution holds up, you're good. You just have to check it at every range. So if I turn this into f of x, and now here is, I substitute x. For x, I substitute t minus t0, right? So x is t minus t0, so it's x plus t0. Now dx is dt, right? Because this is a constant offset. And I continue on. Factor out the part that is not x, right? This comes out because it's not a function of x now. So I can pull that out as constant in the time domain. And here I am going in the x domain, but it's still between minus infinity and infinity. And that comes back to just simply multiplying by the time domain e to the minus j omega t0, right? And t0 is a constant, so this value is going to be a constant. I shouldn't be too surprised by this result. So the Fourier transform of e to the minus at u of t is 1 over a plus j omega. We can look that up in our table of stuff. And then the Fourier transform of omega is now this. Okay, where we're just multiplying multiplying nicely by what we got. Where was our original here? E to the minus j omega t0. I'm finding out what it is I need to do my multiplication here. Yeah, I skipped ahead here. So here we're looking for the transform of what our f of t is e, the shifted e to the minus t minus 2. So my shifting is 2 of u of t minus 2. Okay. And so I'm finding that by saying, well, here's my shifting operation. So the transform of all of this was f of t, right? And I go back and do the shifting of what I know. Well, here is the unshifted form, and now I'm going to shift, right? So what happened? Just trying to locate my pen here. Just a minute. Whoops. So this is the shifted of that. This is the shifting of that. All right. And I know by just taking the unshifted form, I multiply 1 over, if my A was 1, here's my shifting amount, right? And here's 1 over, here's the original one, right? So this gets back to exactly what was predicted up here. All right, on to the next property. Our next one is frequency shifting. And we're saying the result right at the outset. If I take f of t and I frequency shift it, right, is the transform of the frequency shifted one. What is that? We're going to see. Is it just this? So this is the end result, and what we're saying is what the frequency transform of the Fourier transform. If f of w is what the Fourier, that's the Laplace. The Fourier of it's this. I'm trying to make that character of f of t. Right, the Fourier of that. Fourier of f of t is big F of w. Then this is true, right? So what is this? What is this really saying? Let's look at the end result. It says if I do frequency shifting, right, this is the frequency shift. Frequency shifting in the time domain results in phase shifting, right, in the frequency domain. Let's take a little closer look. Oh boy. All right, let me get my eraser going here, which I seldom get to do. So frequency shifting in the time domain results in phase shifting in the frequency domain, okay? And here we have that. So here is the, we're just going through the math steps of this now. The Fourier transform of f of t e to the j omega t, right, is equal to, let's just develop a Fourier transform. That's all that's happening here. We're just multiplying our Fourier effort, right? This was always there, right? That's how we got the Fouriers. And here's the shift portion. Okay? And that amounts to what? Multiplying things out, we get on the underneath here, we get f of t e to the j omega 0 t minus this. So we're just going to add these coefficients, right? So that'll be minus j omega. Minus times a minus is a plus. So this just collected these two terms, right? Mathematically pretty easy. But once we have that, we already know that that Fourier transform is this, with this as the new omega. just a shifted version. Okay? As an example, we took advantage in linearity to create the sine Fourier transform of the sine. Let's say our time function is the cosine of omega 0 t. We did this before, right, with Euler's identity. Right, we used Euler's to get this. So we break it up into that. So it's already looking a little suspicious, like there's some frequency shifting going on. And what does this say? If we take the Fourier transform, if we take the transform of this side, here is that, right, doing that, 1/2 the Fourier of the individual parts, right? And we now know, because of what we just did, this is equal to 1/2 of a shifted plus the shifted in one direction plus the half shifted in the other direction, right? This is shifted in the forward direction, this is shifted in the minus direction, but in the frequency domain. Okay? How does that look? So this is the amplitude distribution, right, of the signal itself, right? In the amplitude, we're doing as a function of frequency here. So amplitude as a function of frequency over the bandwidth, right? That's what we have for the cosine. And now we're saying if we do frequency shifting, in other words, amplitude modulation, we get this. We get something that's half the value in amplitude, right, at each amplitude, so even the peak is half. But now we've got distributions on both sides of the zero axis, right? We got this one here went over here, and we have the other side of it as well, which goes over here. So that's the frequency shifting that takes place, and you actually are splitting. We'll learn in the down the road a little bit. These are called sidebands, right? There was a center frequency here, and these have now been pushed aside, and they're called sidebands. That's a term you'll become more familiar with, especially if you stay with signal processing and perhaps electrical engineering. But these mathematical ideas occur in a lot of places. But this one is especially prevalent in electrical engineering. All right, let's go on to the next one, time differentiation. Okay, so this is, as it shows here, we're dealing with what? The derivative of the time function. And the end result is going to be that it's j omega times the Fourier at omega. This is looking a lot like the Laplace, right, where we had s, f of s, in the s domain. Yeah, not surprising. Okay, so the function is the inverse of the inverse of the Fourier function in the frequency domain. So if that's 1 over 2 pi, and it is the integral of f omega, right, then the derivative of that, so here we take it now, is going to be what? We're taking the derivative of this far right side. So the derivative of that will be the function times e to the j omega t d omega, but it's just the j omega out front, right? If I take the derivative of this, I'm really just taking the derivative of this. So we're left with, if I pull that out, or I recognize underneath, I'm sorry, that this, whoops, is our original f of w, right? Then I've got this times that, and so the Fourier of my derivative is just j omega, keeping the imaginary j omega times the Fourier of the function itself. The nth derivative, since we're always into the math here, we go on with n. As you might imagine, each function, each derivative function, could be treated now as a new function that would then get multiplied by j omega. So the nth derivative is simply going to be the nth multiple, the nth power of j omega. All right. So taking this as an example, if my function is e to the minus t times the step function, the first derivative, minus a e to the minus at u of t, plus what, e to the minus at times the delta function, right? And it's pretty easy to see that the unit step function, right, is this. So you know this, the derivative of this, right, how do I want to say it? The derivative of that sharp edge gives rise to the delta of t, right? So you kind of know there's going to be that piece, and then there's going to be this constant portion in general anyway. So maybe a good visual way to imagine this is what the derivative of a unit step is going to be. And after pulling things together, well, here we are. We recognize we have the original function again, which was this, plus e to the minus at times the unit step. This is all a consequence of the fact that I pointed out here. You introduce a delta function as a result of the step in magnitude. Okay, and finally then, for this example, if we go back to our original supposition, which is that the Fourier of the differential is j omega times the original, that would be j omega times the original is j omega times the original function, the non-differentiated one is minus plus 1, right? And that transforms to the function of what, 1 over a plus j omega. And so this, if I'm solving for f of w, this gets solved. That's all that's going on here. For f of w, right? My solution to that is this, factoring out f of w on both sides, right? I get a plus j omega when I bring that over there and divide that across. That's how I get this. All right, more properties. So let's proceed then with time integration. So here is the result from time integration. We're not going to do a proof of all this, but notice what it is. Remember, we have, if the Fourier transform of the function of time itself is f of w, and I think I'm going to try to write this until I get it, until I'm able to do it, right? Of the function of time itself. If that's true, then this says the Fourier transform of the integral of the function is that function divided by jw plus the value when omega is 0, so that would be the DC value, applied as an impulse. All right? So one thing we can observe, if we go back to the definition, okay, this is the result of putting omega equals 0 into the definition of the Fourier transform. Whoa. Right? This results. Remember, that was f of t times e to the j omega t, e to the minus j omega t dt. But if omega is 0, e to the 0 is going to be 1, and so it reduces to this, right? And you can, so this is the DC component, and if you look at this integral, if the function is, say, a known item that has no DC component, like a sinusoid, all right, the sine of t. We know this has no DC component, and if you integrate this between minus infinity and infinity over all time, you end up with 0. Right? If there is in fact an offset, if the function has an offset, right, so that maybe the function of t is this plus some constant, right, this will break up into two integrals, right, the integral of the sine of t dt plus the integral of k dt. Right, so we will end up with some constant number here, but we certainly don't want it to be infinity. This will have an e to the minus j omega t on it, right? So if we fill all that out and omega is 0, this portion will go to 0 and you'll have a constant. But that's to be expected, right? If I build in an offset, I expect to see it show up in the Fourier transform. So that's allowed for right here, a non-zero one. All right? Take as an example the Fourier transform of the unit step, right? This we know. We can look it up in our tables. That's why we're doing this example. That's equal to the Fourier transform of the integral of the impulse function. Okay, so we're going to find this according to, right, according to this. Right? So what is it? It's the integral of the delta function. So the Fourier transform of the delta function is 1. So here's that first term, f of omega over j omega. And then the second term is just if f of 0 is 1, right? Because it is. You have pi times the delta at whatever the omega is. Okay. Let's try another one here called reversal. Reversal is pretty straightforward, actually. It simply says, if I reverse time, then I reverse frequency. Okay? This is what I would call a one-to-one relationship. If I reverse time, I reverse frequency. And that's also equal to the conjugate, right? Remember that? The conjugate of the response. These, of course, are true provided we have the same initial condition over here. If we know the Fourier transform of the function in time, and we reverse time, then we reverse the frequency domain response. And you can imagine with our splitting, right? Our side lobes in the frequency domain, if as long as those are symmetrical and the same, flipping them isn't going to matter. If they're asymmetrical, then it might. All right. So let's take as an example that if I take 1 is u of t plus u of minus t, right? So what is this? If I have, let's plot this just to make sure we know what we're talking about. So here's the u of t, and I'm making it at 0, but it doesn't have to be, right? And here's u of t we know, right? So that's u of t. And u of minus t, right, is going to be the flip of this. So I'll just do this. Right? And if I add those two, I get the constant 1. Right? That's what's being expressed there. Okay. So what about this with reversal? We're saying then that the Fourier transform of 1 is equal to the sum of the Fourier transforms of u of t and u of minus t. Okay, and we've this we know, and we know how to do this, right, with time. We know how to do that. So here's our Fourier transform of u of t minus the one for minus time, right, is we just said is the same as minus w. That's what we're saying here in our example, in our reversal. So if we add the two, right, we've got our 1 over j omega. So this is the positive. This is this directly. And this is now plugging in minus omega. So this minus comes from having put in minus omega. And here is minus omega, right? So we just put those two together. And if we go through all the math, this nice part cancels this part, and we end up with twice pi times the impulse function, right? So believe it or not, and it is kind of amazing, the Fourier transform of 1 is related to the impulse function, right? 2 pi. I'm just restating it, but it's kind of amazing. All right. So duality is simply stated here by this. We'll just do a quick look-see at how you might get to this. If the Fourier transform of f of t, right, is f of w, right, that's this side. If the Fourier transform of f of t is f of w, then by duality we're saying the Fourier transform of the Fourier in the time domain is equal to 2 pi times the function of minus omega. So the function in the frequency domain, or the minus of the frequency domain. So let's see how we might get to that. So here's our function of t, and it has a Fourier transform f of omega. All right, so the inverse transform of f of omega is just this, right? This basically is the definition. The inverse transform of the transform is back to our definition of the Fourier transform, but our definition in time, right? So we're back to this, but now things are in terms of w. All right, simple math. We're just cleaning up here. So 2 pi times the function of t, multiplying this over there. All right, the integral remains the same, but now it's just the integral of the Fourier transform in the omega domain, e to the j omega t d omega. We're integrating over omega. All right. Now, if we substitute minus t, we're looking at this. All we're doing is putting in minus t right here. So then we put in minus t up here. So all we've done here is substitute minus t for t. Okay, just doing this. It's not like, ooh, some big cosmic reason. We're just doing this because this is going to lead to duality that we want. All right, and now we say substitute omega for t. Now substitute omega for t. We want to take the dual approach. Okay, to omega for t. So now 2 pi f of minus omega is equal to, we're just plugging and chugging here, just reversing t and omega. So here's f of t now instead of omega, and e to the j omega t, that stays the same, dt, right? Substitute omega for t on that side, and sub t for omega on this side. Okay, but if I look at this and evaluate, I say, well, what have I got here? I have got the Fourier transform of the Fourier in terms of t. Okay, so all right, so that's kind of basically the description of what's going on. That's what we have. Whoops, right here, 2 pi. Right, so this whole thing relates back to this thing, and that was the duality statement to begin with. All right, let's take an example. For example, if we have an f of t equal to an f of t equal to e to the minus the absolute value of t. Okay, we know, we can look it up in the table, that the Fourier transform of that will be this. All right, this is just something we look up in the table. I didn't derive it or anything like that. Then by the duality property, if we want to know the f of t, we should be able to just use our formula here, right? And it should be 2, well, that's what we have, 2 over t squared plus 1. Okay? So duality would say that if this is, by duality, right, the transform of this is going to be this. In other words, we just went up here and said it will be, we just swapped the meaning of t and w. So here's our original. We had to multiply it by 2 pi, like it said to do up here. And that's equal to the Fourier transform, 2 pi f of w, right? All right, here's an example very related to one we just did with the unit steps and the impulse function, right? This we can look up as well, but if the time domain function is the impulse, right, at 0, you can look this up, right? It's just in our pre-done table of transform pairs. So the Fourier transform of that is just 1 at all the frequencies, right? And by the way, before we leave this, isn't this kind of to be imagined? If this is our impulse response, if the impulse response, where am I at? Over here. Oops, here I am. If the impulse response, remember, if we started with, whoa, like this, we did this with the periodic wave, and we pushed out the period. We pushed them further out and further out there so that it looked more like a non-periodic wave. What happened? We increased the number of frequencies that participated in the Fourier transform. Well, taking that to the limit is what the impulse response does. This thing shrinks and shrinks till you just have an impulse response of magnitude 1. And look what happens to the frequency response. All of the frequencies are present in equal magnitude. Remember, we were getting this kind of a thing going on, and then it was getting, and more of these were getting filled in, and this was getting flatter and flatter the further out we pushed the period. Well, the limit of that is the impulse response, and it turns out you have all the frequencies in equal amount. All right. Here's one that we really just did. If we have, in the time domain, if we have a constant 1, and remember, we could make this up. We just did this out of this plus this, right? 2 unit step functions, right? It was the sum of u of t plus u of minus t. And that's what's going on here. It turns out the transform of that is an impulse. Well, this is also demonstrated or can be seen or appreciated with duality. All right, let's go on to our last one, which is convolution, of course. The most interesting and maybe also the most difficult. So let's take a few steps on this and see where this goes. All right, remember from earlier, we have the simple system, and with our X excitation, so something like this, right, where the system is described by H, the output is Y, and the excitation is X. This was the convolution integral, right, back in then. Time domain, convolution, and it's the integral of H and X. Okay? The Fourier transform of that will be, very nicely, the multiplication of H and X. Okay? So the possibility here is that convolution in the time domain becomes multiplication in the frequency domain. Okay? So let's check this out. If we look in the frequency domain, we take the transform, right here. We take the transform of both sides of this. So here's the left side, just simply stated. And the right side is now, this is the definition of the transform. Here was the function inside that we're transforming. This is what we transform. This is what we transform. Here's the setup. Multiply by e to the minus j omega t dt, and take that integral between minus infinity and infinity. So we've traded it for the double integral here. Okay? And now we're just going to exchange the order of the integrals. Right? So we're pulling out, we're just moving some things around. Since they both have the same limits, we pulled out our h of lambda, right, and said we're going to take that out separately. And there was a dt, right? So we moved the dt inside and moved the d lambda out. And when we did that, we got rid of the term that doesn't depend on time, right? So there's that, and these go together because they depend on time. All right, that's what we did there. And now from the integral inside the brackets, right? This one inside, well, we see the brackets. We're going to let t, we're going to exchange t for tau, right? Where tau will be t minus lambda, right? These are standard moves, right? We've done this already before. We're going to make this tau equal to t minus lambda. So we'll substitute that there, and that means, so here comes that, and that changes what's up top in the exponent of e. And then we have, instead of dt, we've got d tau. And we can do that because t minus lambda is a constant in the time domain. So this would just d tau. dt becomes d tau straight up. That's good. And now just following through the math, we end up with all of this, right? This is, here's our inside, we have two independent integrals, right? The product of two independent integrals. H times e to the j omega lambda, d lambda, and integrate that. And then x, right? We've just taken x times tau and substituted that. All right? But these are now, this is what? This is that one, and this guy is that term. Okay? So now let's show this. Let's illustrate this on the next page. All right. So what happens here? We're going to start with the convolution in the time domain of two functions that we know. And we actually did this back when we were talking about convolution the first time. So here's the same function, h and x. It's the same function simply because we don't want to get, I don't want to get too expansive, and I don't think the authors did either. So these are two time domain functions, and we know how to convolve these, even in our heads graphically, right? But let's take a look. If I do that convolution, right, I get a triangle of this height, right? The magnitude when they're fully engaged will be a squared times the area, which is 2t0, right? Not hard. And then as they engage, it's triangle. As they disengage, it's linear on this side. Okay, so what about that? The frequency response, right? This up here was a done deal before, right? We've done all that in the time domain. The frequency response of each of those h and t, the frequency response of h and t, we've shown here, right? And they're the same, of course, because the functions are the same. So this is the frequency response down here of that pulse, right? And it's the sinc function like that, both of them. What this property tells us is we can get the frequency response of the convoluted function simply by multiplying these two functions. All right, and so it's the magnitude is the same, right? So it's twice a t0 squared, so we have a bigger magnitude, a rapid drop off, and the null point is 1 over 2t0. Okay, just by multiplying these two. And we know we're going to get mult points because here's the individual function. It's at 1 over 2t0, so that isn't going to move. And it's everywhere along the way like that. Okay? But because it's a multiplication of two identical functions, look what happens. Everything becomes positive here. Everything because it's what? It's positive times positive or negative times negative. This is typical of what happens, okay? But the beautiful thing is a process that was always a little, kind of tricky in the time domain becomes very simple in the frequency domain. So we like dealing with signals that have really cooperative frequency representations. All right, let's go on. So a good question, or one that sort of is sitting in the background, we used to say, well, this all begs the question. If convolution in the time domain corresponds to multiplication in the frequency domain, does multiplication in the time domain correspond to convolution in the frequency domain? Oh my. Well, it turns out this happens to be the case. So let's take it. If f of t is the product of two time functions, okay, so this is our multiplication, and we already did convolution in the time domain. It's multiplication in the frequency domain. Now we're going to do multiplication in the time domain. So here's what we're starting with right here. Okay, this. All right. So if I go ahead and just take the Fourier transform of that, right, that's the Fourier of the product. And we've already been down this road. It's 1 over 2 pi times the Fourier of the first convolved with the Fourier of the second. right? So the Fourier in the time domain, or in the frequency domain, let's just write this all out as though it's real. The frequency of 1, the frequency representation of 1, we'll make it as lambda, times the frequency representation of the other shifted, okay? So, by the way, by shift, I mean I'm just really talking about setting up the convolution integral. So if we go back to the convolution integral, which was a couple of slides ago, and if we replace now the x of t, in other words, the forcing function in that, with the unit step function, okay, that's what's happened here. Right, this was our x of t. So we're replacing it with the unit step. And we're replacing h of t, that would be the transfer response, with the function we intend. Okay, that's our f of t. All right, that is the same as, right, the convolution of f of t and u of t, right? It's convolution. All right. So, but by definition, the unit step function is defined this way. It's 1 when t is greater than 0, and basically when t minus lambda is greater than 0. So wherever the shift point is, the starting point is, it's 1, and it's 0 otherwise. Okay? Well, with this, we can write the unit step now as lambda, whenever lambda is less than t, it's 1. This is just another way of writing the same thing, right? Okay. So we've rewritten the unit step, and if we put those rewritten relationships into this equation right here, if we do that, we get this. Right? We're just applying things into the convolution integral. All right. Now if we take the Fourier transform of both sides, we've got the Fourier transform, the product of the Fourier transforms, because that was convolution. Convolution became the product. Right? Convolution in the time domain became multiplication in the frequency domain. That's what happened on the right. On the left, we've got the Fourier transform in lambda. Okay? So at this point, we're just plugging. So we know the Fourier transform of the unit step. We can look it up, but also we just did it. And the Fourier transform then becomes the Fourier transform of the product here on the left becomes the unit step times the Fourier transform of the function itself. All right, but that's equal to, multiplying it out, FW, this is simply following through the math here, right? FW over 1 over J1 is that, plus pi times F0 of the delta, and we get to use F0. Why? Because we're using the delta function. All right. Well, I flipped to that too soon. So that just is simply saying, yes, multiplication in the time domain, that's what we started with here, is convolution in the frequency domain. Okay, now back. So here's the summation of our properties. These are just straight out of your text. And you know, the authors have put together a number of tables. This is yet another one. If you're going to copy and have anything handy, if you don't have these in a book, or you can't handily look them up online, What's nice here is all of the important ones are present. Here at the bottom is what we've just discussed, actually. The convolution in time, convolution in omega, in the frequency domain. So the relationships, right, between time domain and the frequency domain, the Fourier transforms of all the good ones are right here in front of you. Then likewise, here then are the pairs. So obviously these two are all related, but nice, concise tables that are usable a lot. Because why? Again, almost any function can be broken down into combinations of these in the time domain, and just piecewise then you can come up with the Fourier transforms.